This tutorial is on simplifying Boolean expressions. We're going to start with a simple example, not AB or AB not or AB equals to Y, and we're going to try and map this out to draw a logic diagram. So how would we start that? Well, you can see by this expression that we have three terms that are ORed, so that would result in a simple three-input OR gate. And if we were going to expand it from the right side of that equation to the left, we would probably start with the output at Y, and we'd insert these three individual parts as such, and then we could even further expand this to include the obvious AND gates and inverters that are a part of this expression. We can see that we really only have two inputs and the one output, but this is obviously the middle of this expression. And if we continue on and complete the truth table on the next slide, we'll see something very peculiar. Where have we seen this before? This Boolean expression is identical to an OR gate, which has an expression as such, the A plus B equal or A or B. So we must conclude from this whole exercise that there must be a way that we can simplify this Boolean expression from here to here, because if they are the same output, then they must be the same expression. Simplifying Boolean expressions fall under two different categories. One way to do it is through the Boolean algebra method, which was developed by George Boole in the mid-1850s. And actually his rules and his laws weren't really used in digital logic until the 1930s. The other way is by Carnot mapping. And Carnot mapping was developed by Maurice Carnot, and it's more of a graphical representation of the way in which those ones are mapped out onto a graph, and we'll show you how that's done in a moment. Now we'll be looking at Carnot maps with 2, 3, or 4 variables. There are other ones that have 5 and 6 variables, but we're going to stick with 2, 3, and 4. So this is an example of a Carnot map on the right side, and of course this is our typical truth table. So the 4 squares that represent these 4 different possibilities from the truth table really stem from this combination of 2 inputs, and we know that from previous years and lessons, if we have 2 inputs and we have 2 to the power of 2 inputs, then we have 4 possible combinations. Likewise, if we had 3 inputs, then it would be 2 to the power of 3. We'd have 8 possible scenarios or combinations. So we're going to work with a very simple 2-variable Carnot map. This first square is represented by an intersection of these 2 variables, and we start with not A, and that not A is then translated into A, and not B goes to B. Well, this intersection here where this first square is, where this 1 is the intersection of not A and not B. And if I look over here, in fact, I have A and B. Well, not A and not B is represented by this first combination, which is 2 zeros, because it's a not A, which is a 0, and a not B. And that results in this output being transferred to this square. Likewise, if I look at this intersection between not A and B over here, well, I'm at like a 0, 1. So if I look down here at the bottom, I've got square 1 as not A, not B is 0, 0. I've got square 2 as not A, B, or 0, 1. So you can probably guess where this is going. 1, 0, which is A, not B, is going to be taking up square 3, and then we have this last square to fill, which is simply AB, which is over here on 4, and that square 4 is denoted by 1, 1, or AB. Alright, we're going to complete this Carnot mapping with a 6-step process. We're going to start with the truth table. That's our first step. And we're going to place a 1 in every single one of these squares that represents a 1 output on the truth table. Outputs that represent 0, like this one here, we're going to ignore those completely. So let's take a look. The very first combination we have that has a 1 output is this one right here. So where is that on the Carnot map? Well, we remember that A, if it's 0, as a possible combination with B, which is a 1, that would be a not A, B. Well, let's find that intersection. Not A is here, B is here, and they intersect at this square. So we're going to put a 1 here in this square. Same thing with the next combination, which is A is 1, B is 0, but this B 0 means it's a not B, so A, and where not B and A intersect, we're going to put a 1 right there. And lastly, where A and B intersect, which is this one over here, we're going to put another 1 there as well. Now, I could have started with a truth table, or I could have started with a min-term expression. It's really completely up to you how you want to start that process. Some of you may want to start with the truth table and go right from the truth table and populate the ones. Others may want to start with the unsimplified min-term expression, or the sum of products expression, and start from there. It's really up to you. So let's start with that, and you can see the same thing applies here, that we have the not AB section or part of that Boolean expression, and a 1 is going to be placed in each of those squares that occupies or explains or shows that intersection. So there's that not AB, there's my 1. If I go to A not B, there's A not B, it's going to be down here. And then finally my AB. So I get the same result as if I was to do it directly from the truth table. That should make sense to you. Okay, step 3 is about looping. And looping is just simply circling all of the different pairs or groups of ones that are adjacent to one another. And the way that we loop is we can only loop ones that have 1, 2, 4, or 8 adjacent cells. Now, if we were using 5 variable Carnot maps, then we could go up to 16 adjacent cells. So that should become quite clear to you that the 1, 2, 4, 8, 16 pattern are really just derivatives of the powers of 2. So 2 to the 0 is 1, 2 to the 1 is 2, etc. So because of that, we don't look at 6-cell loops or 9-cell loops. It has to be a factor of the power of 2 there, so it has to be a binary number, 1s, 2s, 4s, 8s, 16s, 32s, etc. You cannot loop diagonally either. So looking down at the rest of this possibilities, or the rest of these possibilities, you'll see that if I was to loop a 1 singular 1, it would look something like that. It's quite simple. If I wanted to loop 2, I could do it in a vertical way like this one, or a horizontal way. And if I saw 4 ones together, I could do a 2 by 2 like this square here, or a 4 by 1 or a 1 by 4. Okay, so you see that they are rectangles or squares there. And then an 8 would involve a 2 by 4, a 4 by 2, a 1 by 8, or an 8 by 1. So the shapes should tell you that you're only allowed to loop in these adjacent cells, and that really results in either squares or rectangles. Typically, unless it's a 2 by 2 here, 4 loop, it's going to be a rectangle. So we go back to our expression, and we've already mapped out these ones on this Carnot map. How then do we proceed? Well, we know that we have a loop that's right here on this vertical space that involves these 2 adjacent ones, just as I have in my example below. And likewise, I have another loop, which is a vertical one, which encapsulates these 2 ones here. Okay, on to my next step of this looping third step. I want to keep looping until all my ones are included inside a loop. That's very important. I can't isolate one and leave it there. And each loop must contain at least one cell not in any other loop. So you can see from this example, I have a loop here, and this one, which is in this cell, is not in any other loop. It's only in this one loop. Likewise, this particular one is in this loop, but it is not in any other loop. So I have to have at least one of those cells that is flying solo on its own. It is not part of any other loop. That's important. Also, intersected loops can allow for further simplification, and you will see right in this example, it's a very good example that shows that this is one loop, this is another loop, and right here at AB, actually it's an intersected loop. So we'll see that that is quite beneficial and simplifies the expression even further. When a cell that contains a 1 is not adjacent to at least one other cell containing a 1, meaning if we have one square that has a 1 in it, and there's no other adjacent ones around it, so above it, below it, to the left or to the right, then that final entry, or that entry rather, in the final expression cannot be simplified at all. And I'm going to show you an example of that in a moment. Alright, on to step 4, where we eliminate variables. This is where the simplification occurs. Alright, we're going to start with this horizontal loop. And what we want to do is take this loop and examine it for a moment, because you'll see that this loop, which is A, B naught, or AB, is this part of the expression that I'm circling here. Okay? And what's nice about this is we're going to use the rules of Boolean algebra that we already used, and we're going to apply them to this Carnot mapping concept. So in Carnot mapping, we want to take these individual variable terms and their complements when they're in the same row or column, and we want to eliminate them. And we use that rule that we've seen before, which is B in this case, or B naught. And whenever you have a B or B naught, or A naught, you're going to result in 1. You're always going to have a 1 there. So if I was to say take this part of the expression, expand it, or factor it rather, and take the A out so that I had B plus or B naught, that part of that B or B naught would be eliminated because it's simply 1, and I would end up with A. Okay, so you can see that A right here is what I'm left with. So I have A or A. Now likewise, if I look at the vertical part of this, okay, and I look at this this loop, you can see that I have A naught B or AB. This A naught and this A can also be eliminated because they're redundant. And that vertical loop means that if I get rid of those A's, I'm going to be left only the A and A naught. I'm going to be left with the B. You can see up here I've taken that out here. Now the nice thing about this expression is that because we've used this intersection of AB twice, we were actually able to take out not only the B but also the A, eliminating this entire middle part. And that's the advantage of being able to use one of these ones 2 separate times. Okay, step 5 and 6 really is just completing this expression. And you can see we've already eliminated the not A, the A, and the B naught. And so what that results in is 2 parts of that expression left, which we OR. So we take this loop, which is a horizontal, which we're left with an A, and we're left with the B on the vertical loop. We OR them together because we have 2 loops. We OR those loops together, and then we simply add our output, which results in our simplified sum of products expression. So if we compare our original expression to our new expression, you can see that we in fact have applied those simplification rules, and we've proven that Carnot mapping actually works using those 6 steps. Let's try a 3-variable K-map. The 3 variable K-map is a bit different now that we know and understand that we have 3 variables. 2 to the power of 3 is 8, so here are our 8 possibilities. But the map is set up a little bit different. And again, I want to highlight something for you here, that it must be prepared in this way. If you look at the way that we start it, this not A, not B, and not C, well, just look at this not A, not B. If you change one of those variables down the left side at a time, and you can never change the same one twice, but you can change one at a time. So what I mean is, if you take not A, not B, and you change that not A, and you invert that again, you're going to end up with B. So you're going to end up with not AB. Okay, now you've already changed that B, so you can't change it again. So change the next variable, which is not A. You're going to end up with AB. Change the B again, you're going to end up with A, B naught. And actually, it'll go right back up to the top if you change the A again and start all over again with this not A, not B. So it's like a little circle there that goes around. Not C goes to C. We only have one variable up here, so it's much simpler to look at. Okay, so this is our min-term expression on the top. Let's map it out. That's our first step. So if I look at this first expression, or first part of the expression, I've got not A, not B, not C. So where is that? Well, simply not A, not B, not C. There it is right there. I'm going to put a 1 there. Next part, not A, not B, C. There's my not A, not B, C. I put my 1 there. And finally, I have my A, B, not C right down here. Okay, so I'm done. So what do I do next? Step 3, we know, is about my looping. So that's what we're going to do next. We're going to loop. And if we look at, again, our guidelines around looping, we can loop 1s, 2s, 4s, 8s that have adjacent cells. So that's what we're going to do. The obvious one is up here, which loops 2 1s side by side. And then I'm going to loop the 1, the solo 1 down here. In a minute, we'll deal with that. Okay, we're going to simplify this very first one on the top by dropping those terms that contain the term, the variable, and its complement. So again, A, or not A, not B, not C, or not A, not B, C. We can see that the C and C naught are the terms that we can drop. Okay, and if you're confused by that, again, if you go back up here and you apply those rules of Boolean algebra, then you can simply factor out the not A, not B, and you're left with not C or C, which is the same as 1. And what does that do? It eliminates the C and the C naught from that part of the expression. And we're left with not A, not B, or not A, not B. Well, that's just simply not A, not B. How easy is that? No simplification is possible for that second or third part of that expression, which is A, B, C naught. So we want to OR the remaining terms, so you're going to OR these two loops. So you have a loop up here, and you have a loop here. So you must OR it with that part that couldn't be simplified and write it out as an output, or as in terms of y, and you end up getting your not A, B, or rather, sorry, not A, not B, or A, B, not C equals to y. And that's as far as you can go with that expression. So it's really important that you notice here, there's no simplification that can occur when you just have a single one like that on its own. Now let's look at a 4-variable K-map. So a 4-variable K-map, as you can see, is a little bit different than our 3-variable in that we have added this D variable, and as a result we have to add a couple more columns. If you look back at your truth tables for 4 input truth tables, you'll notice 4 to the power, or rather 2 to the power of 4 results in 16 different outputs, or 16 different combinations. Likewise, we have 16 different squares here. And the layout of the variables from not A, not B, as we change one at a time again. So we change this not A, not B, we change the not B to B, And since we changed the B, we can only change the A next time. So AB is the next set, and then we change the B back again, and then of course it loops up. Same thing applies here. So not C, not D. We change the D, so not CD, and then we change the C to CD, and then we change only the D again, so we get C, D naught, and then all the way back to the beginning. So let's populate this with our ones, and we're going to go through this fairly quickly as we continue on here. We have A, B, C naught, D naught. So we're going to look down here at A, B, C naught, D naught and populate our ones and go through each one of these parts of the expressions and add our ones. So there's the second one, and the third one is over on the right side of that K-map, and then the last part of that expression is right below the previous one. So we end up with that. Now you might think right off the hop that, well, we simply have to loop these two sets of ones. But what's interesting about the K-map is that if you think of it as a flat piece of paper, we can actually connect those two loops or those two groups of two on either end and actually connect them as a group of four. Now, this is because that K-map can be looked at as a piece of paper that can be rolled almost like a cylinder. So if you think of an empty paper towel roll, and if you were to take your piece of paper and curve it around so that the ends met, then you would have that group of four, just like that picture there with that cylinder. Well, what that allows us to do, because we have one group of four, is we can simplify these variables even further. And keep in mind, because we only have one loop, we're going to be left with no ORs, because we only have one loop. If we had two loops, we'd have one OR. We only have one loop, so that's going to be an expression that's going to probably combine some AND logic, but no ORing at all. So keep that in mind as we progress here. So let's look at the first part. Now this is, again, keep in mind, a group of four. So if I look at this in a vertical way, I am left with this. B's are the same, but A and A naught are complements. So I can eliminate those. And if I go up at the top and look horizontally, I'm looking between C naught and C that I can eliminate. And after I do that, you can see I'm actually left with B on this side and D naught on this side. So I'm ANDing those, and as I said before, I'm not left with any OR. So it's a very simple expression when you compare it to the original one. The last example we're going to show here is another four variable K-map, and you'll notice right off the bat that it's a little bit of a tricky one because we have ones in all four corners. Now you may think that I have to circle all of these individual ones and end up with a massive expression. But again, if you think of this Karnaugh map as a flat piece of paper, is there a way that we can connect those? Yes, there is. We can actually connect it in terms of, or like a ball. So if you connected all four of those corners together, they would actually be connected in one large group of four. Okay, so that's the first step that you need to understand, is that you can do that in these Karnaugh maps. You can turn them or bend them like a cylinder, or again, you can take the four corners in this example and attach them like a ball. That's a very possible thing. Okay, on to simplifying. If I look again at this horizontal area here, or this horizontal area, I'm going to notice something. I've got not C, not D, and I've got not D and C. Obviously, this C and C naught are these two things that can be eliminated. Likewise, down here, these two variables that I have, which are complementary, are A and A naught. So I can eliminate those as well. And what I end up with is simply not B, not D. A equals to y. So we're back at a very simplified version, which is much smaller than what we originally started with. That's all for now. We'll see you next time.